I think it might help if we start by looking at what certain types or certain things in a fluid circuit can do in terms of the Bernoulli equation. Like if we have a section of pipe that has just a pump and that's it, usually drawn as sort of a fan sort of shape. If you think of it as like a propeller spinning within the pipe. So let's say we have a pump and we want to compare two locations on one end and the other. Let's say a location on the left side of the pump and a location on the right side of the pump. If we're comparing the fluid at location 1 and the fluid at location 2, what would we expect to be different about those two locations because of the pump? Yeah, they're going to have different pressure. Everything else is going to be the same. And the way we can see this is by taking a look at the Bernoulli equation. If we write out the complete Bernoulli equation from point 1 to point 2, including all the terms, pressure and potential energy density and kinetic energy density and the pump and the dissipation. Are there any terms here we can ignore if we're just comparing location 1 and location 2?
Kinetic energy density and gravitational kinetic or gravitational energy density.
And why do we know that? Why can we ignore the potential energy density, for instance?
There's no height difference between the two points.
The horizontal pipe, location 1 and location 2 are at the same height. And by the way, even if it's not truly horizontal, like if you've got a pipe that looks like this, as long as the two locations you care about are at the same altitude, then you can ignore the delta y term entirely. There is no difference in height between these 2 points. Even though there's stuff going on in the pipe in between, these two locations are at the same height as each other. So we can ignore the delta y term because locations 1 and 2 are at the same height. And why can we ignore the kinetic energy term?
The area
There's no change in area.
Exactly. The only time these speeds would be different is if the areas, the cross-sectional areas of locations 1 and 2 are different. Since they're the same, that means there's no difference in speed, thanks to the continuity principle. We know the current flowing in matches the current flowing out. And current happens to equal area times speed. So the only way for the speeds to be different is if the areas are different. And also, of course, the fluid has to be moving in the first place. If the fluid's not moving, then there's no difference in speed, even if there is a difference in area. So the only time this term would play a role at all is if the fluid is moving and the two locations have different cross-sectional areas. Should we include the pump term? Yeah, we definitely want to include that because there is a pump on the path from 1 to 2. Of course, there's not a pump at the endpoints, but this side of the equation is talking about what's going on between the endpoints along that path. And what about the dissipation term? Should we include that? Maybe, yeah. The thing is that any section of pipe, even a section of pipe with a pump in it, does have resistance. Every section of pipe technically has resistance. But resistance can often be ignored if it's fairly small. And what do you think about the pipe determines the resistance?
The length, maybe? Like with more length, you'll have more resistance.
Right, the length has a major part to play in resistance. If you've got a very long pipe, it's going to have more resistance than a short pipe if everything else is the same. If we're talking about from immediately on one side of the pump to immediately on the other side of the pump, that's a very short distance. So I would assume the resistance is very small, which means we can probably ignore this. There are some exceptions, like the pump itself does have a little bit of resistance. Even ignoring the pipe itself, the pump has some resistance. And if the current is flowing very fast, then a very fast current times a small resistance is something significant that we can't ignore. But assuming this pump has very little resistance and the current's not flowing too fast, we can probably ignore this term. Which means the entire Bernoulli equation reduces to just 2 terms. Delta pressure equals work density from the pump. Or sometimes we just abbreviate this whole work density term as sort of a cursive E or epsilon. And that's going to be some positive constant. So that means the only thing the pump does in terms of what it does directly to these 2 points is these 2 points will have different pressures. The pump creates a difference in pressure between the 2 sides. It creates a high pressure zone on the side it's pushing on and a low pressure zone on the side it's pulling from. So we have a high pressure side and a low pressure side. And which side is high pressure and which side is low pressure just depends on which direction the pump is pushing. That'll usually be specified with an arrow. Any questions on the pump so far? And I want to emphasize that everything else is the same on these 2 sides. Point 1 and point 2 have the same current as each other, same speed as each other, because there's no difference in cross-sectional area. The only difference is one location is higher pressure and the other location is lower pressure. The pump is pushing to create that pressure difference. And of course, that can certainly have other effects on the rest of the fluid circuit. If you've got other pipes going around, then things could happen in the rest of the pipe because of that pressure difference. But what the pump does most directly is create a difference in pressure. Any questions on the pump so far? Then another important section of pipe, let's assume we're talking about a section of pipe that does have resistance but doesn't have a pump. In fact, let me just clear the board and start fresh. Let's say we have a section of pipe that does have resistance. And let's say there's fluid flowing through it with current I. If we write out a Bernoulli equation to compare the 2 points on opposite sides of this pipe, location 1 and location 2. If we were to write out the entire Bernoulli equation, what are the only terms we actually need to include? The only terms that can't be ignored. Yeah, we should include delta pressure. In general, it's a good idea to include delta pressure unless you know for sure the 2 points have to be at the same pressure. For instance, if both locations are exposed to open air, then they'd both be at atmospheric pressure, so there would be no difference. But in this case, there's no reason to think that 1 and 2 have to be at the same pressure, so we should assume there could be a difference in pressure, because that's often what's there to balance everything else out. We could ignore, once again, we can ignore potential energy because 1 and 2 are at the same altitude. We can ignore kinetic energy density because they're at the same area. We can ignore the pump term because there's no pump along this path. There might be a pump elsewhere, but if it's not on the path from 1 to 2, we can ignore it. So we just have the negative IR term. In other words, what difference is caused by resistance?
A decrease in pressure?
Yeah, this resistance of this pipe, the fact that this pipe has resistance causes a drop in pressure, a decrease in pressure. And that specifically is a decrease in pressure in the direction current's flowing. So the location current is flowing towards is going to be at lower pressure. And the location that current is flowing away from is going to be higher pressure. In fact, that's ultimately what this negative sign signifies here. The negative sign means in the direction current is flowing, pressure is going to be decreasing. Or to put it another way, current flows from the high pressure zone towards the low pressure zone, if you're talking about a section of pipe with resistance. And you can kind of look at that in either direction in terms of causality. You could say that the current flowing through a pipe with resistance causes a drop in pressure, or you could say the difference in pressure is what's causing current to flow in the first place. The causality could kind of go either way. The important thing is there's current flowing and there's a drop in pressure, and those are correlated with each other. And the faster current is flowing, the more the pressure is going to change. Or to put it another way, the more difference in pressure is, the faster the current's going to flow. Any questions on that so far?
Yeah, I have a question. So when they went over the pipe with resistance and it had the 3 standpipes or like a number of standpipes and the water level, like kind of from the FMT, it was higher in the beginning because there's more pressure and then it drops. It said like it was if resistance increases linearly, does that mean like the decrease in pressure is also linear?
Yes, because if we were to take a look at, like, let's say we split up a pipe into several sections. Assuming this is uniform pipe, in the sense that like this entire pipe is, let's say, copper pipe that is 3 centimeters in diameter and has water flowing through it. If all the pipe is the same type of pipe, same width, same type of fluid, and we're just talking about different distances along that pipe, the resistance depends on, among other things, the distance. So if this is if the total pipe has resistance R, then how much resistance would the first half of the pipe have?
R/2 or half R?
Yeah, half of the total resistance. And then the other half of the pipe would have the other half of the resistance. If you've got pipe in series, that is just forming one path, one pipe after the next, then resistance splits up based on distance, and also resistances can add together. If this section of pipe has a certain resistance, and this section of pipe has a certain resistance, you can just add those together to find the total resistance. In series, resistance adds. And what that means in terms of pressure is that if across this pipe you lose a certain amount of pressure, you lose half the pressure in the first half and the other half of the pressure in the second half in terms of the total pressure loss. So if you know you're at high pressure here and low pressure here, you're going to be at some medium in between pressure here. Because as the current flows through a pipe with resistance, it's losing pressure continuously. High pressure, kind of high pressure, medium high pressure, medium low, kind of low, low. It's losing pressure at a constant rate as it flows through this uniform pipe. And every centimeter of distance it flows, it loses a certain amount of pressure. Any questions on that so far?
Does that mean like if you had a longer pipe and it had the same initial pressure and it was open to the air, so it ended at atmospheric pressure, they'd have the same overall total change in pressure, but does that mean the longer pipe would lose less resistance per centimeter?
Yeah, if we're comparing a couple of pipes, let's say a short pipe and a longer pipe. Let's say pipe 1, or let's say pipe A and pipe B, which is, let's say, 3 times as long. And let's assume they're made of the same type of pipe. And I'll say it's all 3 centimeter diameter copper pipe or something like that. 3 times as long is going to mean 3 times as much resistance. But let's say both pipes start at the same high pressure, presumably from a pump or something like that. It doesn't have to be a pump. Maybe they're connected to a water tower, so they've got a lot of gravity feed. So let's say this is high pressure. And then the other end, let's say, is open to the air. So this is atmospheric pressure. And let's say this is also the same high starting pressure. And this end is also open to the air, so it's the same low atmospheric pressure. We could write out essentially the same Bernoulli equation for each of these pipes because they're behaving identically. They're just going to have different values for the variables. Each one of these pipes is going to have delta P equals negative IR. And if you solve for current, what would you get if you isolate current here?
I equals delta P over R negative.
Yeah, and we do have a negative sign because we need to divide by negative R to get rid of the negative sign and the R. So current is negative delta pressure over resistance. And if you're going from high pressure to low pressure, the negative sign is basically just telling us the direction of the current. Current flows in the direction of decreasing pressure. If we treat this as the high pressure as initial and the low pressure as final, not in terms of time, because this whole thing is happening all at once, but in terms of the direction of flow. Final minus initial would be low pressure minus high pressure. What do you get if you subtract a low number minus a high number?
A negative.
Yeah. Delta pressure is going to be a negative value. And resistance is positive, but this negative sign makes the whole thing become positive. So current is going to be positive. And current being positive basically just means, yes, current really is flowing in that direction. If you try to calculate current and get a negative value for current, that just means current is actually flowing in the opposite direction. So we do know current's going to flow from the high pressure zone towards the low pressure zone. Same thing in pipe B. But what's different about pipe B as compared to pipe A?
3 times R.
Right, it's going to have 3 times as much resistance. It's the same pressure drop because both of these are starting at the same high pressure and they're both ending at the same low pressure. So both pipes have the same delta pressure, but pipe B has 3 times as much resistance. If you put in a ×3 multiplier in the denominator, what happens to the result?
The current is 1/3 of the smaller pipe.
Yeah, exactly. The current in pipe B is going to be only 1/3 as much as the current in pipe A. So this is going to have, pipe B is going to have slower current, and we can specifically say it'll be 1/3 as fast as the current in pipe A. 3 times as much resistance, but everything else being the same means 1/3 as much current. Any questions so far?
So because it's slower, that's why it loses less. The pressure decreases in smaller increments.
In terms of per centimeter, yeah. Like if you take a look at a certain section of pipe, let's say you're considering the first centimeter of pipe A and the first centimeter of pipe B. This 1 centimeter of pipe A has some small amount of resistance. The same 1 centimeter of pipe B has the same amount of resistance. So these sections have the same small resistance as each other. If you're looking at just a small section, the rest of the pipe doesn't matter. This 1 centimeter of copper pipe has a certain resistance. This is 1 centimeter of the same copper pipe, so it has the same resistance. So if you write out delta pressure equals negative current times that little bit of resistance, but what do we know about the current in pipe A versus the current in pipe B?
It's bigger, faster.
Right. Pipe A has a larger current. So in pipe A, we've got a fast current times a little bit of resistance. In pipe B, we have a slower current times the same little bit of resistance. So this little section of pipe in pipe A has a certain pressure drop associated with it. The same section of pipe B has only 1/3 as much pressure drop because it's the same little bit of resistance, but only 1/3 as much current. If you look at the entire pipe, it's still losing the same amount of pressure that pipe A does. It's just that that pressure drop is spread out over more distance. So each centimeter has a much smaller drop in pressure, only 1/3 as much.
Okay, that's really helpful. Thank you.
You're welcome. Any other questions on pressure and resistance so far?
Sorry, one last quick thing. Is resistance the same as like losing thermal energy or like friction?
The default term is, yeah, the negative IR, we usually call this the dissipation term.
And how's that related to friction? Like, is that the same thing?
Essentially, yeah. We're talking about the fact that the interaction between the fluid and the walls of the pipe make it more difficult to flow. That if you consider the individual molecules of fluid, molecules that are very close to the wall are essentially not moving at all. They're sort of stuck to the wall and they can't really move. If you look at like the next molecule in, that next molecule can move, but kind of slowly because the molecule that's staying still is slowing it down. And the next molecule in can move faster. It's just being slowed down by the slow moving molecule that's being slowed down by the molecule stuck to the wall. And likewise, on the other side, we've got a stationary molecule, a slow moving molecule. The molecules in the middle are moving the fastest. The molecules near the edge are hardly moving at all. So molecules close to the edge, the fact that they're interacting with the walls are slowing down the whole thing. Or not so much slowing it down, but making the decrease in pressure due to losing energy density. So that is essentially friction. Technically not friction between the fluid and the walls, because the fluid right next to the walls isn't actually moving, but friction between the fluid near the walls versus the fluid not near the walls. And we usually call this pattern laminar flow. The idea of this continuous gradient between fluid near the walls hardly moving at all versus fluid in the center moving very fast. But it's smooth is the point. You've got a smooth transition between hardly moving at all versus moving very fast. If you sort of disrupt that smoothness, if it's moving so fast that the fast flowing water sort of interferes with itself, then you get what's called turbulent flow, and then you get extra resistance from the backblast. But we're assuming laminar flow in this class. Any other questions on that so far? So to sum up, the negative IR term called dissipation overall does generally represent something like friction in the sense that you've got moving fluid that loses energy due to its motion in conjugation, in context with the walls impeding its motion. The presence of these walls and the interaction with the walls makes motion difficult. So it makes it lose energy as it moves. And the resistance depends on several things. First of all, the length. The longer the pipe is, the more the resistance is going to be. So longer pipe means more resistance. What other properties of the pipe do you think will influence the resistance of the pipe? Like if you could design a
area?
pipe, yeah, the cross-sectional area plays a big role. If you have, like, let's say you've got a very large area, would you expect that to be more or less resistance?
Less.
Yeah, larger area means less resistance. Because if you've got a very large pipe, like I said earlier, the molecules near the wall are hardly moving at all. But if you've got a very large, very wide pipe, the molecules near the wall are very few. Most of the molecules are in the interior. So those many molecules that are far from the wall are able to move much more smooth, much more easily. It's only the molecules near the walls that have trouble. So the wider the pipe is, the more molecules are in the interior and are able to flow easily. Whereas a narrower pipe means most of the molecules are near the wall and have a more difficult time flowing. So wider pipe, in the sense of more cross-sectional area, means less resistance. And there's also one other factor that has to do with the fluid itself, the material the fluid is made of. It's essentially the viscosity, how I guess you might say how thick or how sticky the fluid is. So viscosity also plays a role. More viscosity means more resistance. So we can essentially set up a formula for resistance based on these terms. If we combine these together, resistance should be directly proportional to length. More length means more resistance. So if we were to set up a fraction as a formula for resistance, should length go in the numerator or denominator?
Denominator?
If it's in the denominator, would longer length mean less resistance or more resistance?
Oh, that would be less. So
Yeah.
It should be in the numerator.
Right, because we want larger length to lead to larger resistance. So we're going to put the length in the numerator. And we usually call that delta X because the length of the pipe just tells you how far the fluid has to flow. So delta X in the sense of the change in position of the fluid as it flows through the pipe. So longer length of pipe means more resistance. Whereas a wider pipe, larger area, means less resistance. So where should area go in this formula? Yeah, area is going to go in the denominator, so that larger area of the pipe means less resistance. And then the viscosity, and I think to some extent the material the pipe is made of, but mostly the material the fluid is made of, can be summed up as one number called the resistivity. And that's usually written as a lowercase r. So this basically represents properties of the material and how difficult it is for that to flow. So a larger length of pipe means more resistance, larger cross-sectional area means less resistance, and the material the fluid's made of also plays a role. But this gives you a basic formula for predicting the resistance of a section of pipe. So for instance, twice as much length is going to mean twice as much resistance. But something like 4 times as much area means 1/4 as much resistance. So you got proportionalities and inverse proportionalities in terms of length and area. Any other questions on resistance? And you mentioned resistance in parallel also. Let's take a look at what that would be. We talked a little bit about pipes in series. Series in the sense of just joined together end to end. So if you've got like a section of pipe and then it's connected to another section of pipe. Let's say pipe number 1 and pipe number 2. And let's say pipe number 1 has a certain resistance R1 and pipe number 2 has a certain resistance R2. We would say these pipes are in series. In that case, what could we say about if we were to treat this as just one big pipe, what would be the resistance of that one big pipe?
R1 plus R2?
Yeah. The total resistance of this one big pipe, we can just add those resistances together in the sense that any fluid flowing has to go through this much difficulty and then also this much difficulty to get to the other end. So the difficulty levels combine. But what do we know about the current flowing through pipe 1 and the current flowing through pipe 2?
Current change due to the cross-sectional area?
Cross-sectional area causes a change in what, though?
Oh, wait. That would be velocity.
Yeah, there are going to be different speeds. So the speed in pipe 1 and the speed in pipe 2 could be different. But what should we assume about the currents?
It's still going to be the same due to the continuity equation, correct?
Exactly. That whole idea of continuity. For any section of pipe, the current flowing in has to match the current flowing out. Yeah, exactly. I1 equals I2. We could also think of that as at this point where they join together, the current flowing into that point has to match the current flowing out of that point. The currents have to be the same due to the continuity principle. And also, if we take a look at the pressure changes, let's say we've got pressure 0, pressure 1, and pressure 2. Presumably, we're losing pressure as we go through pipe 1. And then from there, we're also losing pressure as we go through pipe 2. So the pressure drops can also add together. We've got a certain drop in pressure from 0 to 1, and we've got a certain drop in pressure from 1 to 2. And those drops in pressure should match. The drop in pressure from 0 to 2 is equal to the drop in pressure from 0 to 1 plus the drop in pressure from 1 to 2. We're just combining how much pressure you lose through pipe 1 plus how much extra pressure you lose through pipe 2.
I'm a bit confused because didn't we say in the last example, I don't know if it's because they were different pipes, but that the one with more resistance had 1/3 the current?
In that case, they weren't connected in series though. In fact, they weren't really connected at all.
Okay.
This is more if we take 2 pipes and weld them together. So it's just one single path.
Okay, so now the current's not affected, even though the resistance is different?
The current is affected by the total resistance, but the current has to be the same through both pipes because there's nowhere else for it to go.
Okay.
Like let's say the current flowing in is 5 gallons per second. You've got to also have 5 gallons flowing out per second because there's no other path for it to take. There's nowhere else for the fluid to drain out. And that's what we usually call the continuity principle, or when we get to electricity, we're going to call the same idea the junction rule, in the sense that at this junction where the pipes join together, the current flowing into this junction has to match the current flowing out of this junction. And that's going to be true for electrical current in the same way it is for fluid current. Again, even though they're different things, they behave in very similar ways. Any other questions on this pipes in series idea? And if we're looking at pipes in parallel, that's going to be something different. Pipes in parallel is more if you've got a single point that branches out into two pipes. Let's say you've got pipe 1. And this might be the same as the original pipe 1. We're just bending it a little bit. And then also splitting into pipe 2, which maybe is also the same as the previous pipe 2. We're just bending it a little bit. And then maybe they merge back together. Which means we're going to have current flowing through both pipes. Current 1 and current 2. Do those currents have to be the same? Not necessarily, because they're taking different paths. These aren't just one path and then another path directly after it. These are two alternate paths. They do both start at the same point. They do both end at the same point. Let me mark those locations, let's say location A and location B. We have current flowing in towards location A. Let's call that I sub 0. That is whatever the current is before it hits this point. And yeah, we can still use the idea of conservation of current. We can still use the idea of continuity. What's the total current flowing into location A?
I0.
Yeah, we've got current I0 flowing in. And what's the current flowing out of location A?
I0, but it's split.
It's split, right? Flowing out of location A. If we ignore what's happening before A, we've got I1 and I2 flowing out. So I1 and I2 together, yeah, I1 plus I2 has to match the current flowing in, I0. We sometimes write that as the sum of the current flowing in has to equal the sum of the current flowing out. In this case, the current flowing in is I0 alone. The current flowing out is IA or I1 plus I2 together. So this is the modified version of the continuity principle. It's still the continuity principle. It's just that the current flowing out has split into two paths. So this is what we get in series, that the current flowing, or sorry, in parallel. If we've got pipes connected in parallel, in the sense that it's two alternate paths instead of just one unified path. They're essentially splitting up the available current. In series, both pipes got the same full current, but in parallel, the current that's coming in gets split amongst the pipes that are involved. And it might be more than two. You might have it splitting into 3 pipes, for instance. Then it would split 3 ways. But in this case, we get the current splits. Current 0 equals current 1 plus current 2. We can also apply the same junction rule at location B. We got current 1 and current 2 coming in. They combine to get I1 plus I2, which is the same I0 again. So the current flowing out the other side is the current that was flowing in the first place. It just splits up into 2 different currents in the in-between region. However, it might be the case that it splits up evenly, or it might split up differently. Maybe one of the currents gets more, one of the pipes gets more current than the other. If they do get different currents, which one would you expect to get more of the current? Or what do you think is going to play a role there?
The wider one, maybe?
Width does play a role. But yeah, ultimately it's all about the resistance. whichever pipe has less resistance is going to get a larger share of the current. The one with more resistance does get some current, it's just less of the current. And that ends up being proportional. Like if this was, let's say, twice as much resistance, if I1 had twice as much resistance as pipe 2, then pipe 2 is going to get twice as much current as pipe 1. In general, the one with less resistance gets a larger share of the current. So when would you expect the current to split evenly?
If the pipes had equal resistance.
Right. If these two pipes have the same resistance as each other, then they're going to get the same share of current. The current would split exactly half and half. Or in a three-way split, it would be 1/3, 1/3, 1/3. But the pipes split up the current equally if they happen to have the same resistance. If they have different resistances, then whichever one has less resistance gets more of the current. But they do, in general, have to split up the available current, and this continuity principle still holds. The current flowing in has to match the total of all the currents flowing out, and vice versa. Any questions on current so far? What about for pressure? If pipe 1 has a certain delta pressure associated with it, and pipe 2 has a certain delta pressure, what can we say about those delta pressure values? Presumably, which one of these points would you expect to have higher pressure? Yeah, we can expect pressure A to be higher. So we've got high pressure on the left side and low pressure on the right side. If you go through pipe number 1, you start at this high pressure and you end at this low pressure. So you've got a certain delta pressure associated with that. If you go through pipe number 2, you start at this high pressure and you end at this low pressure. So what do you know about the delta pressures for the two pipes here?
Should they be the same?
Yeah, they're going to have the same delta pressure because they're just two different paths that start at the same high pressure, go through some path, and end at the same low pressure. So both pipes have the same delta pressure. So delta pressure for pipe 1 equals delta pressure for pipe number 2. And note that this is very different from the series situation. In series, they have different delta pressures, but those add up to the total delta pressure. In parallel, they both have the same full delta pressure. Like if this pressure is 100 pascals and this pressure is 1 pascal, both of them get the full 99 pascals worth of pressure drop. So in parallel, they both experience the same full delta pressure, but they have to split up the available current. In series, they both experience the same full current, but they have to split up the available pressure drop. Maybe you lose some of the pressure through this pipe and you lose the rest of the pressure through this pipe. But in parallel, they're both getting the same full pressure drop. Any other questions on that so far? And then for resistance, if we want to know, because in this case, for a series, we can just add the resistances together. In parallel, though, the resistances don't add, because if you connect several pipes in parallel, if you've got a pipe and then you add another pipe and another pipe and another pipe, creating more paths, would adding more paths make it more difficult or more easy for fluid to flow?
Easier, probably.
Yeah, more paths makes it easier because there's more options. And you could even think of this kind of like as traffic on a freeway. If you've got a freeway that has really heavy traffic, one way to ease the traffic is to provide alternate routes. That way some of the cars can go on the alternate routes. More paths makes it easier for the flow to happen, allows more throughput. So adding more paths is going to make the total resistance lower. The total resistance of this whole network is going to be lower than the resistance of each individual path because more paths makes flow easier. And to calculate the amount of resistance, we can actually use the idea of the currents adding together. Going back to the idea that delta pressure equals IR, I'm going to ignore the negative for the moment. Actually, let's go ahead and include the negative. If we solve this for I, what do we get? How would you isolate I in this equation? Yeah, we divide both sides by R, so delta P over R. And there's a negative there, but it's going to be in all of them. So each one of these currents can be written as the appropriate negative delta pressure over resistance. Current 1, we can write as negative delta pressure over resistance of pipe number 1. Current 2, we can write as negative delta pressure over resistance of pipe number 2. So each pipe has its own resistance, but what do we know about the delta pressures?
They're the same.
Right, we've got the same delta pressure for each one. And I0, the current flowing in, if we just treat this whole thing as one big weirdly shaped pipe, if we ignore the split in between, we can just pretend this whole thing is one big pipe, and current 0 can be written as negative delta pressure. Again, that's the full delta pressure of the whole thing, divided by what we might call a total resistance. So if we think of this whole thing as just having one big total resistance, current 0, the current flowing in the first place, can be written as negative delta pressure over R total. But since it's the same delta pressure in each term, what can we do to get rid of that?
Cancel them out, so it's 1.
Exactly. If we just divide both sides by negative delta pressure, then negative delta P cancels out from every term. And we're left with 1 over R total, because this is still in the denominator, equals 1 over R1 plus 1 over R2. So this is how resistances combine if they're in parallel instead of in series. In series, you just add R1 plus R2 to get the total resistance. But if the pipes are in parallel, instead of adding them directly, you'd add the reciprocal of R1 plus the reciprocal of R2, and then take the reciprocal of that whole thing to get R total. For instance, let's say these resistances are 2 and 3. You add 1/2 plus 1/3, that would get you 5/6. Then the reciprocal of that would be 6 over 5, or 1 1/5, 1.2. So if these are 2 and 3, the total resistance would be 1.2, which is less than either one individually. Because once again, connecting pipes in parallel, adding more paths, just makes it easier to flow. Any other questions on that? All right, feel free to let me know if you have any other questions, and I will see you next time.
Thank you.
You're welcome.